Hello and welcome to this movie on effective currents. A magnetized iron rod can be substituted for by currents that move in certain directions on and in the object. The surface and volume densities of these currents can be determined by these equations shown below. And in this movie we'll be using cylindrical coordinates, which are very helpful for use in cylinders, tubes, rods and wires. It uses the unit vectors K, S and C, where C stands for circulating. S or R are standards for the vector which is pointing away from the axis, and K stands for the vector in the positive Z direction, which is also parallel to the axis. Even though the unit vectors C and S change with the location in space, they can still be worked with as functioning unit vectors. We'll explore effective currents with a number of examples. In this first example, we have to find the surface current density of the rod that has a magnetization of M0 in the positive I direction. The first thing to do is to use the effective surface current equation that is given here. It uses cross-product multiplication. The vector value of the magnetization is M0 times I, where the unit vector I contains its direction. The unit surface vector of surface A is inclined to the base by an angle of theta, so this is the value of the normal vector n to its surface. It can be easily calculated using geometry. Plugging these values into the equation at the top gives us this cross-product expression. And using the rules for cross products, one of which is that a unit vector cross-multiplied by itself gives 0, we get this expression containing the unit vector minus j. And placing the minus sign outside the expression gives us this answer. And here is a picture of what these currents look like on this surface, being in the direction of minus j. And now, considering this bar, we must find the current densities on 3 of its faces, A, B and C. Surface A is now perpendicular to both B and C, and is not inclined. Well, to calculate the current density for surface A, the first two lines are the same, but the unit normal is minus I, which is a very tidy vector to work with. When we substitute these values into the top equation, like we did before in the last example, we get this expression. And because of the cross-product rule that a unit vector cross-multiplied by itself is always 0, we end up with this answer here. There is 0 current on the surface A. And to calculate the surface current for surface B, the first two equations are as before, but the unit vector is now equal to K, pointing upwards. And after substituting these values into the top equation, we get this expression. And using the cross-product rule, we get this result. And this is a picture of how the currents travel on surface B in a negative Y or J direction. And now to calculate the surface current density on surface C. The unit normal vector is minus j. And substituting these values in, we get this expression here, which gives us this answer here after applying the cross product. And here is a picture of the surface currents for surface C. Notice how they act to circulate the current around the bar. It can be shown that the surface currents make a complete circulation around this bar. Now to find the surface current densities around this short solid cylinder. To find them for surface A, we plug in all the values for the surface A, including the surface normal vector of A, so as to get this result of 0, because it has the same surface normal vector as the bar that we've analysed just before. Similarly, surface B has 0 surface current density. On surface C, however, the surface normal is S everywhere, because we're using cylindrical coordinates. ijk coordinates would be much messier for this case. Plugging the values in gives us this cross product equation. Notice that S is always perpendicular to K, and should give us an answer as a whole number of m0 times another unit vector. And so it does. Its direction is in C so as to circulate around the rod. And here is what the surface currents look like on surface C. And now we must calculate the volume current density of this solid cylinder. We use this equation, which is the definition of volume current density. We plug in the value of magnetization into it. And because the magnetization is the same in all positions of space inside the rod, its curl is 0. This solid cylinder has a magnetization that does have a non-zero volume current density. To calculate its volume current density, we use the equation and substitute the magnetization into it. And here is what the curl looks like for this value. It looks very complicated, but can easily be done on a computer. And here is the answer being non-zero. And now here is a second example of a magnetized solid cylinder that would have a non-zero volume current density. And then we plug this value of magnetization into this equation like we've done before. And it gives us this partial differential expression. And it gives us this value which is non-zero. The concept of effective currents can be extended to a large number of other types of vectors. The first example is of a surface current that could be substituted for a polarization vector. If a magnetic field could be caused to slowly increase over time in a direction so as to circulate around a long rod or cylinder, then it could be a sort of surface current density that could be substituted for this polarization. Similarly, a circulating constant magnetic field could be an effective surface current for a magnetic vector potential vector through a hollow iron rod. And similarly, a slowly increasing electric field could be a second effective current for a magnetization vector. But they won't get confused because magnetization vectors are almost never caused by increasing electric fields. This is because after a long time, the electric field would have to be extremely high, and a lot of electronics would be necessary to do it. Magnetized iron rods can exist almost forever and without any special electronics.